honorable members of IAPT, the experts, invitees, and all the participants. I myself, Dr. V. Rajeshwar Rao, on behalf of RC22, just I am giving a welcome remarks for the third day. So far, we could listen to wonderful lectures on day 1 and day 2. That includes some superposition, and in the second day we entered into qubits. The two lectures were very interesting, and many participants also they participated in discussion. So the things are moving in a wonderful manner. On behalf of RC22, I'm feeling very happy. As my friend Madhusudan is traveling, he requested me to make a beginning with this welcome remarks. As just I hand over to Vandana Luthra Madam to proceed further. Thank you. Vandana Madam.
Good evening to everyone. Again, we welcome all you here. Thank you, Professor Rao, for your kind introduction. And today we are beginning with another exciting session by Dr. Jyoti Qc. It is my privilege to again introduce her to all the participants. And with that, I'm just doing that. Dr. Jyoti Qc, who is a PGT Physics in PICT Model School, Bhelwadi, Pune. She is an enthusiastic physics teacher, and she has a total of 13 years of experience. That includes 9 years of engineering college and 4 years in a junior college. She has worked in Priyadarshini Engineering College, Nagpur, and in Cummins College of Engineering, Pune. She was university topper with her graduation in year 2003, with a recipient of 9 gold medals and 2 cash prizes. She completed her PhD from VNIT Nagpur, and she has cleared SET GATE exams. She is passionate about physics learning and believes that physics is a subject of experimentation and keeps motivating her students for more and more hands-on activities. So with this, we invite Dr. Jyoti for another interesting talk on how to create superpositions, part 1. Over to you, Dr. Jyoti. Thank you.
Thank you so much. Thank you, ma'am. Very good evening to all of you. I take this opportunity to present session 3 today. So I will share my screen. Please let me know whether the presentation is visible to you.
Yes, it's visible to us.
Thank you, ma'am. Today's topic, it is session 3, creating superposition, and I will be discussing the beam splitter. In first session, as we have...
It is visible, ma'am. You can continue.
Yes, thank you, sir. So, out of these 9, we completed first 2 sessions till now. One is introduction to superposition. Another is what is qubit. Yesterday, it was beautifully delivered by Vandana ma'am. And today, I'm taking the third session, that is creating superposition, the beam splitter. Now, let us revisit or let us recap what we did in first 2 sessions. First session, we talked about superposition. We understood or we tried to define superposition with the help of, say, 2 waves, various examples like electric field or forces or electrostatic potential, or simple day-to-day life example like when you are swinging on a swing and your friend is applying force in the same direction or in the opposite direction. So superposition means whenever two physical quantities they are added, now that addition may be vectorial addition because the physical quantities like force, displacements, they are vectors. So it will be vector addition, or they may be algebraically added, like for physical quantities like electrostatic potential, that will be algebraic sum. So that will result in a pattern. There will be addition of amplitudes or there will be subtraction of amplitudes. And we have seen it through simulations, through GeoGebra, by considering two waves and how they superimpose. Suppose crest of one wave falls on crest of another, or trough of one wave falls on trough of another, there will be addition of amplitudes. If crest of one falls on trough of another wave, there will be a subtraction. So if the amplitudes they are equal and opposite, you will get 0 as the resultant. I even demonstrated the simulation of two light waves where they superimpose and they undergo constructive and destructive interference. And on the screen, we can see alternate bright and dark spots. So we talked about classical superposition and we defined the state, that classical state, which is always a definite state. Then we switched over to quantum systems. Quantum systems are always, their world is different. They are microscopic systems where Newton's laws, Newtonian mechanics is not following. So new theory is proposed. We talked about Planck's quantum theory. We talked about quantization, and we discussed several physical quantities out of which are quantized, which are continuous. And then we defined what is quantum superposition. So in the very first lecture, as you all know, that we defined the quantum systems which can exist in superposition state, with each state having some probability. We talked of probabilities. There we discussed an example of Schrodinger's cat. It is a thought experiment, and you will consider the cat, whether it is alive or whether it is dead. You will not be able to find out unless and until you open the box and peep inside and see the actual situation. So in that case, unless and until you see, till that time, it is in the superposition state with both states possible, multiple states possible with some probability. We talked of flipping of the coin. So when we flip the coin, when it is in the air, it can either show head or tail with 50-50% chances, 50% of probability. But once the system is measured, the superposition, it will collapse the superposition and you will get one definite classical state. In session 2, Vandana ma'am beautifully explained classical bits and how various electronic circuits we design, like gates we use to get the 0 and 1, the bits. And then she beautifully explained the superposition of both the states with probability and the use of ket, the operator ket, and how to represent the state. Now, in today's session, what we will learn is how to create this superposition state. Like if we flip the coin, we can imagine, we can see that it is in the air, but we cannot, means we will get 50-50% probability of getting a head or a tail. But how to create such superposition states? For that, we need some real physical examples. So there are several, out of which today we will be talking about photon in a beam splitter. So we will basically discuss what a beam splitter is and how the superposition state is created using beam splitter. In tomorrow's session, you will learn another experiment, which is Stern-Gerlach experiment with the help of electron, how the superposition state can be created. There is one more experiment, which is double slit experiment, where also we can use the constructive and the destructive interference, and we can create a superposition state, giving two possibilities. So let us now focus on today's topic. What is a beam splitter? Now in this, in classical optics, a beam splitter acts like a partially reflecting mirror. Suppose this is a mirror and the mirror is visible to you, and you can see that the light which is incident, it is 100%, intensity is 100%, then it is partly reflected and partly transmitted. If it is a semi-transparent, so partly the light will be reflected and partly it will be transmitted through. You can see a day-to-day life example when you are, say, traveling in a train, you can see the things outside and you can see your own reflection. So we can take that as an example of beam splitting, that partly the light is reflected back to you and partly it is transmitted. So we say 50-50% chance of getting a reflected beam and a transmitted beam. Now, what exactly is light? Whether it is a wave or a particle. This I discussed in the session 1 also. I would like to revisit, I would like to tell one more time that depending upon which experiment we are performing, whether we are talking about reflection of light, refraction of light, or we are dealing with the interference of light, or we are talking of polarization of light, it is where it shows wave-like properties, it is a wave. Whereas if we are considering the experiments like photoelectric effect, Compton effect, if we are dealing with the atomic spectra, if we are talking about the transitions like Lyman series, Balmer series, in session 1, I gave the example of hydrogen atom and quantization of energy. So if the electron is making a transition from higher energy level to lower energy level emitting the photons, so where you are getting the spectral lines, so which phenomenon or which situation you are dealing with, accordingly the behavior of light will change. It will behave like a particle in some phenomenon, it will behave like a wave in some phenomenon. Classically, light was thought as a wave consisting of continually oscillating electric and magnetic fields. You can see in this figure the electric field vector, which is represented in red arrows, and magnetic field vector with the blue arrows. They are perpendicular to the direction of propagation, which is x direction, and they are mutually perpendicular. So this is called as an electromagnetic wave. Light is consists of electromagnetic spectrum. And another experiment, the light can be thought of as stream of particles called photons. Now we need both these pictures, both these theories while dealing with beam splitter. So let us see how. So wave nature of matter, as we have seen this de Broglie hypothesis, he saw the symmetry in the nature. He again considered that light, if it exhibits dual nature, same should be true for material particles. So this is just a revisit. Let us move ahead and let us see this simulation. Now, I want my audience to go through the simulation very, very carefully. I will play the simulation. You have to look at it and what are the things that I will explain, what are there in the simulation, and then you have to answer this question. So we will again see the question later. So I'm just changing the screen. I will open the screen where you will see the simulation. Just let me know whether you are able to see the simulation. Build a Mach-Zehnder interferometer. Is the screen visible?
Yes.
Yes.
Yes. Thank you so much. Now this is in the introduction part. There are two parts. One is introduction, another is controls. So in the introduction part, if I bring the cursor on each and every component, it will give a short description of that. For example, this is a photon source. Its energy is 2.8 electron volt. So you can send a photon and you can see what happens at beam splitter 1. Now what is a beam splitter? It is an arrangement, say a glass, and it is coated with a dielectric. You can see this blue slab, and above it is a layer of dielectric material. Now, what is a dielectric material? We will discuss in detail after seeing the simulation. Okay. So first thing, in the beam splitter, it is a half silvered mirror that converts the photon into superposition state of being in both the upper and the lower paths. So what will happen? The photon, it can take a path after reflection. It can go, it can transmit. As I said, partly it is reflected, partly it is transmitted. There are two mirrors placed over here, which will reflect the beam, which will direct it to the second beam splitter. Now, let us come to the controls. Let us first deal with the first beam splitter. Let us see what happens over here. So what I will do, I will fire a photon and you have to observe. Then I will put the question. Then you will write your answers in the chat box. Okay. So when I fire first photon, where the photon is received, partly it is reflected, partly it is transmitted, and you will see that it was received in the first detector. I will again play. You can see the photon is received in the first detector. One more time. Okay. If I'm doing it a continuous fire, so how it will look like? It is showing the photon. One more time. Just observe the simulation. Now, once you have observed this, I will stop the continuous fire and I will return back to my presentation where the question was, which detectors are triggered when the photon passes through the 50-50 beam splitter? I will give you 30 seconds to write your answers in the chat box. Okay. So you can write your answers. You can write options A, B, C, D. Yes, my audience is smart enough. They have observed the simulation very nicely and they could answer that yes, the detector 1 or detector 2. The photon was sometimes collected in detector 1 or detector 2. Okay, thank you so much for such a quick response. Let us move ahead and see the second question. Now, with the same simulation, which detectors would trigger if a classical wave is sent through the beam splitter? Now, imagine that in same simulation you have to imagine. Initially, I am talking about the photon and you could see that it is detected either in detector 1 or detector 2. Now, if I imagine it as a light wave, we have talked of both the pictures, light as a wave, light as a particle. So when it is a wave, it will be partly reflected, partly transmitted. So what you expect in the output? Which detectors would trigger if a classical wave is sent through the beam splitter? So I want to see your answers. Yes, now the answer has changed to D. Some are saying it is B, it is both, it is A. So the correct answer is D, that it will be triggered in both the detectors, detectors 1 and detector 2, because it is showing a wave nature. Fantastic. Let us move ahead. So your answer is option answer D. Okay. Now let us move ahead to the third question. Now, which detectors would trigger if a classical particle is sent through the beam splitter? Now, again, I'm talking of a particle, a classical particle. I'm asking the same question, which detectors would trigger if you use a particle nature? Please write your answers in the chat box. Now, there is a mixed response, but the answer C, yes, I can see the answer C written, many of you have written C. So you will see that if it is particle nature considered, again, the detector 1 or detector 2, you don't know, but then there will be equal probability of getting the particle in 1 or in detector 2. Let us address one more question from this observation. What does the photon do at the instance it encounters the 50-50 beam splitter? What is happening to the photon when you are receiving, when the detectors, your answer was detector 1 or 2. So what was actually happening to the photon? Whether it was splitting in half of the photon is transmitted, half is reflected, or whole of the photon is going through and with the 50% probability and reflects with 50% probability, or whole photon is both transmitted and reflected essentially in two places at one time. So let me check the answers. Yes, fantastic. Just clapping for you. That answer is B. and you have understood the concept. So whenever we are talking of the photon, we are saying it is having 50% chance of getting reflected, 50% chance of getting transmitted. Fantastic. Thank you. So the answer to this question is answer option B. The whole photon goes through with 50% probability and reflects with 50% probability. Okay. Now, what are our observations? We are saying that photon, if the photon was split in half, both the detectors would be triggered. That is not happening. As only one detector goes off at a time, the photon could not have split up. In this case, we see that light behaves more like a saucer ball, more like a particle than like a water wave. Means here we are talking of particle nature, predominance of particle nature of light instead of wave nature. So just like how a spinning coil will land on heads 50% of time and tails 50% of time, same here we have observed that a single photon is in a superposition of both the states all the way, but you don't know, you cannot predict whether it will reach to the detector 1 or it will reach to the detector 2. Okay, so this is our first observation. Now coming back to this, in yesterday's session, Vandana ma'am has given a description of how the state is written. Like ket photon, it is 1 by root 2 ket 0. So let us say this is for transmitted path. Let us say for the transmitted path, its state is represented by 0, and reflected path, it is represented by ket 1. So we can write the equation as 1 by root 2 ket 0 plus 1 by root 2 ket 1. So of course, what is the probability? How do we calculate the probability? We talked about these are alpha and beta. We talked about the normalization condition. So alpha square plus beta square is 1. So what will be the probability of getting photon transmitted? 50%, 1 by 2. What is the probability of getting photon reflected? Again, it is 1 by 2 or 50%. Yes, the phenomenon of superposition allows quantum computers to perform operations on 2 bits of information at once with a single qubit. So what is a qubit? What you learn? Can anyone put in the chat box a summary, a precise definition of yesterday's session? What is a qubit? What is a qubit? They are quantum bits. So how quantum bits are different from classical bits? Yes, fantastic. It is quantum bit. So how quantum bit is different from classical bits? What was different? Superposition of 2 states. Fantastic. Clap for you. Yes, so you have understood the concept that whenever we are talking of quantum states, quantum bits, we are always talking of superposition of 2 states with some definite probability. That we have to always keep in mind, right? So using photons as qubits, beam splitters are used as to create superposition. Our topic is to create superposition. How we will get multiple states where the photon can go. So we need some assembly, some device which will split the photons into 2 states, multiple states, and pieces of glass that will slow down the photons along the selected path. Now, this is something very important, phase shifters. Yesterday, in first session, someone asked me what is phase. What is meant by phase? So we will be talking about in detail about phase today, and we will be using that when we are adding one more part to our simulation. Okay, so moving ahead, let us add second beam splitter in our experiment. I will repeat the simulation for you. I will show you the simulation and I will repeat it one more time. And this time I will add one more beam splitter into that. That device configuration is known as Mach-Zehnder interferometer. And this setup is very sensitive. There the distances between mirrors and detectors, which are the same or which have to be same or differ by an integral number of photons wavelength. So I will return back to that screen and I will show you the simulation again. Here, just let me know whether the screen is visible, where I'm showing the Mach-Zehnder interferometer.
Yes, it is visible.
So I'm firing the photon. This is very first simulation, first part that I have seen. and you answered that both the detectors, detector 1 or 2, will receive the photon. So sometimes it will be detected in 1, sometimes it will be detected in 2. It may so happen 3, 4, 5 times it is detected in first detector, and after that it will get detected in the second detector. Or if I fire continuously, I can see the effect. The photon is going. So unless and until I'm talking of the particle nature of light, then I'm getting the detector 1 receiving it or detector 2 receiving it. Now what we are doing, we are adding here mirrors, and we are adding one more beam splitter into this. What is the function of or use of the mirrors? It will direct our beam. Basically, the beam which is reflected will fall on mirror 2 and again get reflected. It will get directed to splitter, beam splitter 2. The beam which is transmitted, again there is one mirror placed over here from where it will be reflected. Again, these two beams or two photons, they meet over here, and then what will happen? So let us see this simulation. So I will fire the photon. And now you have to observe. Again, I will ask you questions. One more photon. One more photon. One more photon. You collect your observations. If it is a continuous fire. If it is a continuous fire, the photon which is transmitted, reflected, and is going through the second beam splitter. Okay, let me ask the question based on this. Okay. So we use second beam splitter. You have observed the simulation. Now you have to answer what is happening. So if we assume that the photon was reflected by first beam splitter, which detectors would be triggered? Please write your answers in the chat box. I can see the chat box full of messages. Yes, fantastic. Everyone is writing. Since it was clearly observed by all of you that answer option A is correct. So if I just show here the answer, you will see that it is always detector 1 which was triggered when the photon reaches over. Now here, this is very important. We are assuming that the photon was reflected by the first beam splitter. I will come to that later again. Now, let me ask you another question. If we assume the photon was transmitted by the first beam splitter, here comes the role of mirror 1 and mirror 2. You have seen that when it is reflected, it is incident on mirror 2. And when it is transmitted, it is incident on mirror 1, which is again directing it to the second beam splitter. So which detectors would be triggered? So please type your answers in the chat box. You have seen for the both the cases. Yes, your answer is not changing. You are getting it this time also. Always the detector 1. The photon is collected in detector 1. Yes, thank you so much. Now, if we move ahead, let me ask you one more question. Now, this session is more of questions, and then we will arrive at the conclusion. You yourself will be able to tell me the last conclusion or result, what all experiments or simulations we are playing and what we are exactly arriving at, right? Construct the Mach-Zehnder interferometer in the beam splitter simulator and fire a single photon. Which detectors are triggered? Now, what will be your answer? Again, you recollect what we did in the simulation. Shall I play the simulation one more time? Fantastic. You are able to answer without seeing the simulation. Yes, the answer is A, that again, you are getting the photon detected always in the detector 1. Fantastic. So your observations are all correct. Whether the photon is reflected, whether it is transmitted, it is always collected by detector 1. Now, the first question that comes to our mind is why? why this is happening. What is exactly happening over there? Okay, so let us go ahead. So our observations are a photon was either transmitted or reflected by first beam splitter. It would have 50-50% or 50-50 chance of transmission or reflection by second beam splitter. You only have answered the very first question that it will be detected either in 1 or 2 when only first beam splitter was placed. Now, when you are adding the second beam splitter, the situation changes and you are every time getting the photon in detector 1. There is no case when it was detected in detector 2. So we want to find the answer for this question. Okay, let me give you some time to guess the answer. What can be happening? What must be happening over here? The reflection coefficient is less since it goes for reflection 2 times. No. Okay, we will come to that later. Guess the answer. What must be happening over there? Interference. Partly correct. We will have to go into the details of that. Yes, and it is correct. But what way, which two photons or which two waves associated with the photons are interfering? Constructive interference. Okay. Fine, fantastic. So let us move ahead and first let us talk about phase. I have promised I will explain you what phase means. Let us take the simple example of simple harmonic motion and uniform circular motion. Now, some of you may not be knowing what is simple harmonic motion, the technical word, but if I just say the swing machine of needle moves up and down, to and fro motion, that is called as simple harmonic motion. You will learn in higher classes why is it called as simple harmonic, what are harmonic functions. But now, if I just take an example that this particle P is performing a uniform circular motion. Okay, I will show over here. I will just I will just highlight this part, that particle P. I'm talking about this particle. It is moving in the anti-clockwise direction along the circumference of the circle. Now its shadow is P dash. Its shadow is P dash. So when P moves in the anti-clockwise direction, it reaches over here. So you can see where the shadow will move. It will move in this direction. And when P is here, its shadow comes over here. P dash. Agreed? Now, when it reaches over here and starts following this path further, there is one more point when it is reaching over here, its shadow comes at this point only. It comes at P dash only. Means you are getting actually 2 points, P, let us name this as P dash and P double dash, where their shadows coincide. It is just as P. So here the position is same, but what parameter is different? The parameter different is phase. Phase is also defined as state of motion. Means here you can say the particle is moving further anti-clockwise, but as it reaches over here, it will go, means the particle P dash is moving to the left, but with respect to P double dash, now its shadow is moving to the right. Means their phases are different. We will be talking about phase every time when it comes to superposition of two waves. And in session 1 simulation, when I said crest falls on crest, we are talking of same phase. Crest falls on trough, phases are different. They are out of phase. So phase is different. Their state of motion is different. With this background, now let us understand what exactly is happening in our simulation. So we are considering the, okay, before that, let me play another simulation to explain how the reflection of waves takes place. So I will just play this simulation. Okay, fine. Just let me know whether my screen is visible. Okay, it's taking time to open. Just a minute. Yes. So is the screen visible? Here you can see a wave pulse traveling on the string. Yeah. So if I consider the reflection from a hard boundary, so what is happening? Just observe. What is happening? A crest, when reaches to a point, now this point is fixed. It cannot move. There is a rigid surface, rigid wall. So when a crest is approaching, it will be reflected as a trough. So there is a phase change of 180 degrees. Phase, again, I'm using the same word. The state of motion is changing. Initially, it was the particles were moving in the upward direction. Now they have started moving in the downward direction. So there is a phase change of 180 degrees on reflection. When is this happening? At the hard boundary. To put this in more scientific technical words, if the transverse wave is incident from medium of low refractive index into a medium of higher refractive, we call rarer and denser medium. So if the light is incident from rarer to denser, at the denser, it will reflect and there will be a phase change of 180 degrees. Okay. Now, let us consider the soft boundary. What happens opposite? You will see that when wave reaches at the soft boundary, the rarer medium, it will just oscillate. The force is always in the upward direction. So it will oscillate and the crest will be reflected as a crest. A trough will be reflected as a trough. And therefore, there is no phase change as for the incident wave. Now, these 2 points we have to keep in mind. Let us return back to our presentation. I will repeat it one more time. When the light wave is incident at the denser medium, where refractive index is more, there is a phase change of 180 degrees. And when the light wave is incident on the rarer medium, there will be no phase change. These 2 points we will now apply in our present case. Okay. So I will go back to, right. So we are talking of the first beam splitter, which is consisting of a glass. And as I said, a dielectric medium over there. We are saying it is partially silvered. We are putting a coating on the glass. So how that coating is? The refractive in that coating is dielectric medium. Dielectric medium is actually basically an insulator. You will more learn about it in higher classes. But for now, you have to just remember that the refractive index of air is less than refractive index of dielectric, that is less than refractive index of glass. So what happens when the light is incident from air at the interface? It is entering the dielectric and is incident on the glass medium. You can see here. You can very clearly see over here. I'll just highlight. I'm talking about this wave, this particular case. This ray is incident at the interface. This interface is of dielectric and the glass, and we are saying dielectric is of lower refractive index than glass. Means the light is incident at the denser medium. So definitely when it reflects, there will be a phase change of pi radian. Means if it is a crest coming over here, then that will be reflected as a trough. You will get a phase change of pi radian over there. But if you are considering this ray, this particular ray, which is coming from below, from glass into the dielectric, or say at the interface of dielectric and air. Here also you can say glass and dielectric, which is denser, glass is denser. Dielectric is of lower refractive index. So when it reflects, there will be no phase change. Again, remember, when it is transmitting, there is no phase change. So phase change will only occur upon reflection. For transmission, there is no phase change. So when the light enters the beam splitter from dielectric side, the reflected light is phase shifted by pi. Light entering from glass side will have no phase shift. This phase shift will occur only when light enters from lower to higher index of refraction, medium, dense, rarer to denser medium. Now, keeping this in mind, let us again revisit our simulation. What was happening over there? So if we assume that light is a classical wave exhibiting interference, can you work out which detectors would be triggered? Note that the first beam splitter has a dielectric side on the top, while the second beam splitter has dielectric side on the bottom. I think I will show the simulation one more time so that you will get an idea. So I will just show the simulation one more time. See, the first beam splitter is having the dielectric on the upper side. The second beam splitter is kept upside down, exactly opposite. Now I fire a photon. So look and tell me what is happening. You are getting output again in 1. So if you think of a classical wave picture, then how will you explain getting the output only in the detector 1? Okay, so let us come back and let me show you the question. If you assume that light is a classical wave exhibiting interference, can you work out which detectors would be triggered? Note that first beam splitter has a dielectric side on the top, while the second has dielectric on the bottom. Now, please type your answers in the chat box and let me see what answers you are getting. Fantastic. You are getting the correct answer, and that is answer option A. It is always detector 1. So how it is working? Here, the beam splitter, the photon source which is sending, the second beam splitter treats the photon as if it come from both top and the bottom simultaneously. First beam splitter, it will reflect and transmit. For transmission, there is no phase shift. For reflection, you will see where the dielectric is. So if you remember, I had shown in the simulation that dielectric is on the upper side. Okay. So if the dielectric is on the upper side, it is entering from glass into dielectric. There is no phase change for this beam. So you can say there will be zero phase change for both the transmitted and the reflected wave. When it comes to mirror 1, it is reflected. When it comes to mirror 2, again it is reflected. So if it is 0, 0, and there both the phases, again it is air to glass, so you may say phase change occurs, that will be equal for both the mirrors, right? And when it arrives at the beam splitter 2, now it is upside down, means the dielectric part is on the bottom side and glass part is on the top side. So you will see that it is entering from dielectric into glass. So it will be phase shifted. Transmitted one will not be phase shifted. So you will find that there is a phase difference of pi radian for the two rays or waves coming in the detector 2. There will be destructive interference. Their intensity is cancelled, and every time you will get the photon in detector 1. Okay. I hope this explanation you all have understood. We are talking in terms of classical wave. We are considering the wave picture of light, and we are using the concept of phase shifting upon reflection. So when the light is incident from rarer into denser medium, the phase will be shifted by pi radian. When it is transmitted, there is no phase change. And when it is going from denser into rarer medium, there is no phase change. Okay, fantastic. I think this much is clear to all of you. Let me check what you have understood. Now, let me ask you one more question. If the photon is sent into Mach-Zehnder interferometer from the upper left instead of bottom left, I will just come back to the diagram. I am saying the photon source was placed below. Now, if I change its position and I am keeping it on the top, and the beam is incident from the glass slide instead of dielectric. So, which detectors would be triggered and with what probability? Please type your answers in the chat box. Think and type. I will show you the diagram one more time. We are saying the beam, the photon source is kept on the upper side, and the photon is entering from glass into the dielectric The dielectric, as I can see here, is on the top. So the same diagram, only the we are changing the photon source. It is coming from dielectric side. So think and write your answers. Oh, there are 15 chats. Okay, I will just check the answer. So what is happening when it is coming from upper left instead of the bottom left? Which detectors would be triggered and with what probability? And the answer is always detector 2, because the things are reversed. Now, whatever was happening at detector 1, exactly opposite thing will happen at detector 2. Detector 1, their phases will be out of phase by pi radian, and there will be destructive interference, and the waves will be in phase at detector 2. There will be constructive interference, and they will be detected at detector 2. Okay. Now, considering all these simulations, what is our conclusion? What we are trying to arrive at? So in the Mach-Zehnder experiment, we created superposition, perform a phase shift, and then observed wave interference. These experimental operations are equivalent to mathematically applying matrix or gate operations on a qubit. Yesterday, if you remember, Vandana ma'am has shown various gates, NOR gate, XOR gate, OR gate, AND gate, and how we were giving the inputs and how we were getting the outputs classically. Similarly, Mach-Zehnder experiment is one possible arrangement where we can create a superposition. Here, if you see everywhere, I'm talking about photon. We are considering the classical picture, but whenever we are talking of the results, we are saying probability. Okay, one more thing I would like to show you. So I will go back to the simulation. The very first simulation where I'm considering, I will remove the second beam splitter. I will remove the mirrors. The very first case here, when I fire the photon and we were getting the output in 1 or 2, this shows the quantum states and this shows the theoretical probabilities. Now the picture is more clear that single photon, which was which was incident on a beam splitter, it created multiple states, 2 states. It can go in detector 1 with 50% probability. It can go in detector 2 with 50% probability. So beam splitter is creating superposition. It is giving us multiple states with definite probabilities. 50% chance of getting the photon in detector 1 and in detector 2. Now, when I insert mirrors and insert the second beam splitter and we apply the phase consideration over here, we find that the probability becomes 100% because every time the photon is detected in the detector 1. If you reverse the cases, you will get detector 2. That was what my last question was. So with this simulator, you just play with this. You can play with the simulator and can explore various options, and you can see how the quantum states, different quantum states you can create, and how can you write the theoretical probabilities. Here, every time we are writing 1 by root 2. Why? Because 50-50, we are considering 2 states and they have equal probability initially and then 100% for the last case. So in conclusion, what we are trying to draw from all these simulations is, using beam splitter, we created a superposition, we performed the phase shift, and then we observed the wave interference. These experimental observations, they are equivalent to mathematically applying operations on a qubit. Why we are all doing this? We want a real life application where we can create multiple states. Like if you remember in the beginning of my lecture, I just gave an example of a coin which is flipped. And I said when it is in the air, it will have definite, say 50% chance of getting a head or getting a tail. But we cannot create it. We cannot show it experimentally that this was head or tail. When we are using Mach-Zehnder interferometer, we can actually see the transmitted beam and the reflected beam, and we are creating a superposition And then we are adding one more beam splitter and seeing how the phase shifting is happening and how the waves they interfere to give you the outcome. Similar way, you can use these experimental operations. They're equivalent to mathematically applying operations on a qubit. So we can create multiple states using beam splitter. As such, the Mach-Zehnder is an example of how we can technologically implement qubits, which means photons, and the operations. So here operations means we are talking of the superposition or phase shift to build a quantum computer. Now this is very basics. We are learning the first step, how the superposition states are created, right? So when this base is made, further studies, further sessions will be easy for you. So how the superposition state is created, one method is beam splitter. As I said, in the next session, you will learn more about another method, which is Stern-Gerlach experiment. That also you will enjoy. So in quantum computing, people talk about superposition of states rather than wave behavior, but it was easy to work on waves and get the means we could imagine by considering the wave nature. So as we have seen, both the frameworks that led to the same understanding of Mach-Zehnder interferometer. So this is all about today's session. If any questions from audience, they are welcome. Thank you so much for patient listening.
Thank you so much, Dr. Jyoti, for the wonderful talk. There are some questions, but I would like to first make a summary of what you have done. It was the superposition states you talked about, reconsolidation on the definition of qubits as a superimposed state. After that, you talked about that how to generate using a beam splitter. That was really very nice using this simulation. And then different conditions which you showed with the help of simulation. And these simulation, all the participants, please note, we will be sharing to you and you can try on these and you can understand more while you are at home. So we will be sharing all the simulations by today and you can practice these at home. And then also you talked about the mathematical representation in the matrix form, which can be done with the help of any programming language like Python or Scilab can be used for that. Yesterday, we couldn't do that session, but definitely those who are knowing programming language, they can always do it. So we have some questions here. So thank you so much, Dr. Jyoti. We have some questions here. There is one question which is by, I'm not remembering, Krishna Kumar Muthuswamy. He's asking, tell us about alpha and beta in the notation. So in the first slide, you were showing alpha and beta. So please, you can answer this question.
Yes, I will share the screen again. Is my screen visible?
Yes, your screen is visible.
So as we discussed yesterday also, we talk about probabilities. Just a second. Yes. So if I am representing any state as alpha cat, like I gave an example of Schrodinger's cat. So whether the cat is alive or whether the cat is dead, there we are defining these alpha and beta as the coefficients which tell us the probability of occurrence of that state. For example, one more slide I showed where we actually represented the probability, this one. Yes. So here the photon, the transmitted path, if I'm representing the state by say ket 0 and reflected path by ket 1, I'm writing the alpha and beta since it is equal probability, which is 50%, 1 by 2, 1 by 2. So alpha and beta are the coefficients that tell us the probability of occurrence of that particular state. So here the value of alpha will be 1 by root 2, value of beta will be 1 by root 2, and we follow normalization condition. We say alpha square plus beta square is always 1. So 1 by 2 plus 1 by 2 is always 1. I hope you have got what you have asked.
Yes, very nicely explained, Dr. Jyoti. And the next question is why Dirac notation is used?
That is for representing the state. How will you represent any state? Just like you write some equations, so you decide some conventions that this has to be written. If I want to represent the state of photon, how the photon is. So this is one representation given by Dirac.
Yeah, this is one representation. May I add to this, Dr. Jyoti?
Yes, please.
Actually, it is also coming from inner product. In the inner product, it is a bra notation followed by a ket notation. And when we are using bra and ket, actually we are dividing the scalar product. So those who are studying it in their colleges and at higher studies, I think they can also, and it is a sort of convention as told rightly by Dr. Jyoti. Thank you so much, Dr. Jyoti. So we have another question. I will start reading from the chat. What are some, this is by Virendra, what are some practical applications of beam splitters in quantum technologies?
Pardon?
What are some practical applications of beam splitter in quantum technologies?
So as I said, the beam splitter is used to create superposition. The qubits which we are studying, how we will get the quantum bits, the bits in multiple states with some definite probability. So one way of getting it is beam splitter. Another experiment that you will learn tomorrow is Stern-Gerlach experiment that we use for electron, and we will talk of electron spins, spin up and spin down. So again, electron in spin up with 50% chance, spin down with 50% chance. So beam splitters are basically used for getting the superposition, create superposition.
Thank you so much. We have another question by Yugen Kulkarni. If we are getting fixed output at detector 1, why to use superposition?
No. In this particular case, after adding second beam splitter, because that we are trying to show how that is getting converted into a definite state on adding a second beam splitter. Actually, the first beam splitter is creating a superposition. Second beam splitter, it is giving output only in detector 1. So that is the beauty of the, the experiment or the simulation, that how it is creating multiple states, and then by shifting the phases, how it ends up only getting output in the detector 1.
Thank you. And there is a request by Mr. Sanket that please share the link of the reflection simulation. So Sanket, we will be sharing all the links which ma'am has shown today. Please, it will be sent to either the WhatsApp group or we will send it through the email. There is another question by Dr. Bhupendra. Ma'am, is it possible reflection from air to dielectric boundary?
Air to dielectric is possible, but in this particular case, we are considering dielectric and glass. So glass is denser than dielectric, and whatever reflected, means it is 3 layers actually: air to dielectric, dielectric to glass. So where the reflection will occur, the waves which will be reflected from glass that we are considering, so they are phase shifted by pi. And if you consider opposite, that they are entering from glass and reflecting at dielectric interface, that is going from denser into rarer, there would not be any phase change upon reflection.
Thank you. And do we have any other question? I think majority of the questions have been taken care of. Let me just again check the chat. Dr. Jyoti, if you go back to the simulation, I would be requesting you to show something which can be taken up by those who know the programming language, because this is a very mixed group. We have got undergraduate students as well as teachers. So if you click on show matrix representations of optical elements, the last one, if you click on that, yeah. So one can show here that how does mathematically the matrices can be written for a beam splitter, for a mirror, and all these things. How do these work? So those who are at a higher level and they are
Exactly.
learning programming languages, they can always explore this. This simulation is going to be with you. Play with it, try to understand, and in some cases, Beam Splitter can have other configurations other than 50-50 also. So that way, it will be depending upon the engineering that how you construct it. So this is an open, say, box in which you can always explore so many things, and you can get back to us if you want to even learn something more than the basic which we are telling you. And thank you, Dr. Jyoti,
Right.
for wonderfully answering all the questions. And
Thank
I
you.
assume that there is no more question in the chat. Let me do that because some
I have
more
one
are
question.
ending.
Ma'am, I have put the link for this link for the Google form, which will have some 8 questions. They can attempt the quiz.
I have one question, if you can explain.
Please,
Yes, sir.
Consider the case of a toss of a coin. Then what are the values for qubit? It's 0 or 1 or 1 by square root 2. So there are 3 values. Am I right?
Pardon, I did not get the question.
Consider the case of a toss of a coin.
Toss of a coin, yes.
Yes. So what are the values qubit can have? It's 0, it's 1, then 1 or 1 by square root 2. 3 values.
So that we discussed in the very first session when the coin is flipped.
That-
When the
Oh.
coin is flipped and the coin is in the air, it will have both the states possible with 50-50 probability. 50% of getting a head or 50% of getting a tail. But unless and until it lands on the ground, you will not be able to tell. So that quantum superposition collapse, and once you measure it, and it will be a definite state with a head landing or
No,
landing
my
with a tail.
point is it can, that means it can have 3 values. So
When it is
instead
in
of,
air, it will have 2. When it is in air, it will have 2 states possible. One is head or tail with 50% probability. 1 by root 2 as value of alpha. Alpha, beta, 1 by root 2.
and
Yeah,
actually,
there are some more. Yes, please continue. Sorry.
how many values are there? 0, 1, and 1 by root 2, 3 values.
No, sir. In this particular case, let me say, if it is head showing, we assign suppose 0 state. If it is tail, it is 1 state. But when it is in air, it will be a superposition of 0 and 1 with alpha 1 by root 2 and beta 1 by root 2. The quantum superposition will exist when the coin is in the air. When once you measure it, once it lands on the ground, the superposition will collapse and you will see the definite state that it is either head on the coin or it will be a tail. So you can clearly say that it is 0 state or 1 state.
Okay, then how it differ from classical bit? Bit also contains 0 and 1. What is the difference between the two?
No. That what we are trying to get. No, classical one is 0 or 1. Just like low voltage, if we assign 0 state, high voltage is 1 state. There is no state in between classical bit. But when we are talking of quantum, we are creating superposition. We are creating 2 states simultaneously. The coin can be in head or tail unless and until you measure it. So we talk in terms of probability. We talk in terms of chances. But again, that is quantum superposition. When you measure it, it will collapse to definite state.
Okay. Then what is the advantage of qubit?
Name.
That is how qubits work. That is how qubits work. By
I mean,
creating
that means it holds more information than say, classical bit.
So this is very basic. We are just understanding how a quantum superposition is created using beam splitter. But if you go in more details for application, you will get several other factors. This is just the basics. When it comes to application, like there is one session where we will talk about the encryption of data. You're using WhatsApp and you're sending message to some of your friends. So you receive a message that your data is encrypted from both the ends. So there are other factors several other things you have to add to this to use it in the application.
No, I thought that it hold more information than a classical bit.
No, not like that. Like in mathematics, sir, high school children, they learn about algebra, then geometry, and then comes the calculus part. So they are using all the basics there also, but then they keep learning more and more. So several more other factors will get added to this when you are actually learning some application.
Thank you, Dr. Jyoti. There is another question by Dr. Saha. Won't there be any change of phase when the photon beams are getting reflected on mirrors 1 and 2?
Yeah, but that will be equal. That will be same for both. If it is going from air to glass, means again it is reflected at the denser medium. The refractive index of glass is more than that of air. So the phase is changed, but that phase change will be same for both the beams.
There is by Abhilasha Shukla. We can determine which detector will detect the photon depending upon the position of dielectric and glass. Then how come it is considered in quantums, which is purely probabilistic?
So the second beam splitter is actually we are getting the output only in detector 1. First beam splitter you cannot tell, you are telling the probability of whether it will go in 1 or 2. That is the beauty of the simulation. That will add few more terms into that, few more factors.
Another by Dr. Mukherjee. If we can make logic gates either with 0 or 1, then how can we do the same thing with qubits?
I did not get your question.
I repeat, if we can make logic gates with either 0 or 1, then how can we do the same thing with qubits?
Qubits is more advanced. That will increase the speed of your operations. That is what we are using in quantum computers. So classical bits, there is a restriction. Like as I said, there are several factors. We are just studying the basics. This is first step of creating a superposition. Once you understand this, go to the next level, like that. So when it is application, you will explore more based on the same basic principle of creating superposition, but some advanced applications.
Yeah, thank you so much. And there are some more questions which have come up. And should we answer it now, or can we take it for the email
We
to be
can take
answered?
it, ma'am, later, I think.
Yeah, because everyone has to fill in that quiz also, and that will take 15 minutes.
Yes.
So these questions can be noted by us, and we can try to answer those to them over the email. Will that be fine? Please, the organizer, please tell us that what to do.
Is there any time for filling up the Google form?
They can fill in next 15 minutes and submit. They have to take quizzes for all the sessions. That is mandatory for getting the certificate. So it's better if they can click the link and fill it right now.
And later, actually, I could not fill up yesterday. It was closed.
Okay, we will see that. If it is closed, we will open it for you again so that you can take the quiz.
Cannot fill up yesterday, so that's
So today you just fill it right now so that there will not be any delay.
okay. Actually, I have sent a mail. I have sent a mail that I could not fill up the form.
I was thinking that we can note down these questions. So, I think in the YouTube chat, it will be difficult to note that. So
they can put these questions on the group, WhatsApp group that is created.
WhatsApp group also,
yes,
right?
yes,
They can
yes.
put their
So
questions.
all these questions can be sent to us on email, or it can be posted on the WhatsApp group, so that we will try to answer as far as we can in all the cases, all the questions. So we will request you to kindly fill in the quiz. That is more normally for 15 minutes, but we can extend for 5-10 more minutes so that everyone can fill it. And those who have missed yesterday's quiz, I think we can make it 90%. 9 quizzes are mandatory. So in that case, if in case you have missed it, only one, then it should be fine. So with this, I can invite Professor P.K. Ahluwalia ji for his remarks on today's talk, and followed by Dr. Reshma. Thank you very much. Thank you, Dr. Jyoti, once again for the
Thank you,
wonderful
ma'am.
talk.
Thank you so much for your support. Thank you.
So thank you, Dr. Jyoti, once again, very clear exposition you gave. And I think for most of the participants, listeners, viewers in this Zoom meet, these must have been new things only. These are not something which are very well known. To tell you very frankly, this nomenclature, different names which came up for creating these qubits, I heard for the first time. I never had this exposure. So that is what it adds to. The only thing which I can say is that the language of all these transformations in terms of the beam splitters basically are undertaken through some kind of a transformation matrix operating on some kind of a state. So once we start defining those transformation matrices, we will immediately understand mathematically also that how these transformation matrices lead to a particular kind of a qubit. And it can be seen as some kind of a matrix operation where you are multiplying a 1x2 matrix with a 2x1 matrix to get some kind of an answer. Say one is alpha beta, say a row matrix, and another is say 1 0, and then you try to operate on that, and you know that now with one state alpha will be multiplying, and with 0 state beta will be multiplying, and you can play with these alphas and betas, leading to different probabilities for state 1 and for state 0. So suddenly we find, and if you go to even optics books, I will particularly refer to Professor Ghatak's book on optics. You will find that they talk about these coefficient matrices for, say, reflection, for refraction, and so on, particularly in the context of ray optics. These are very well-known things. There was another thing which I wanted to mention. Maybe you must have said that, but I somehow or the other must have missed it. That beam splitters have been there for quite some time, right in the very beginning. Michelson-Morley experiment also actually makes use of beam splitters only. So that is the first instance where people get to hear about beam splitters, but we never really try to think there the way we were thinking here in terms of the now photons. Actually, that was the difference. There we were saying, okay, a beam has been, there was a wave coming, it got split into two waves, which we call, with the help of which we cause interference. That was what we were doing that. And there we were trying to see something happening in one direction and something happening in a direction perpendicular to that to get the interference pattern. So the best part of this whole story is this, that the ideas of what people are doing in quantum optics leading to the formation of qubits has been there for quite some time, but it took lot of effort technologically to achieve those kinds of situations which Jyoti ma'am was actually trying to explain. I think once again, I may say that I enjoyed this. I also need to understand very many things which are being talked about. So slowly and steadily, the what has been discussed in this lecture, it will start sinking in once we start looking at it again and again and again. And fortunately, our videos are, reusable objects. Once again, I'm using this term. Start listening to it till you understand fully. You can repeat that portion where something is being explained. And what the role of dielectric is, how dielectrics actually interact with electromagnetic waves. These are very fundamental questions which we need to really look at. So thank you. Enjoyed it. Great, ma'am. I'm sure that future lectures are going to really also keep us glued to this particular program. Thank you once again.
Thank you, sir. Thank you so much.
Yeah.